turning effect of force. We studied that we use the force to accelerate the body. We use the force to pull and push the body, right? Or we use the force to increase the velocity of the object, or we use the force to stop the body. But other than that, we also use the force to rotate the body. For example, you can use your force to rotate the object. I'm trying to rotate this pen, right? And there's one point here, and I am applying the force in the other end. And there is a other thing is the distance between this point and the force applied, right? How far I am applying the force. If I am applying here and here and here, this effect, turning effect, will be different. And that quality of the turning effect we also call the moment. And the moment can be measured using the force and the perpendicular distance from the force to the point, this point. And how does the direction of the force? Suppose I'm turning this pen here. I'm applying the force in this direction, right? And if you move a little bit down and down and down, the direction of the force will change. In order to calculate the moment of force, what actually we need? You can see in the sticky notes, the moment of force is equal to the force and distance, multiply force with the distance. So we need two things: perpendicular distance and how much we force apply. In this example, you can see the range. This range, this is the range, right? And we apply some force here in this directions. We can see how much we force apply, and this is the perpendicular distance from here. This is the point where we see the turning effect. This is also called pivotal, and this is the distance from the pivotal point to the force. This is the direction of the force, and this is perpendicular distance. And torque is equals to force into D. But actually we don't know the D, but we know the angle. Look at here, in this example. So this is the range and F, and we need a perpendicular distance. This is a perpendicular distance, which is called D. And how you calculate this? Suppose this is theta. Theta is the angle between the length of the range and the force, right? And we know that we apply the distance L from the point. We can measure this part. So D, how we can measure the D equals to, right? Because the sine theta equals to in this triangle perpendicular distance by hypotenuse. So D equals to L sine theta, and from the definition of torque we know that F is F here, which is the force, and D is L sine theta. So if we measure how far we are applying the force, we know that this distance and how much we apply this force, and we can calculate the turning effect of force. This is simple. And where is the maximum? Torque max will be when theta is 90. When you apply the force in this direction, when theta is 90, your torque will be maximum. And it will be 0 minimum when theta equals to 0. Means you are applying this direction. You can rotate this object because you're applying the same direction, right? So when theta is 0, there is no turning effect here. And in this case, this force is uh, perpendicular from this pivotal point. In this case, tau equals to, you know that this distance uh, f is equal to the uh, f and d. Here theta equals to 90, and f is, if this is weight, you can say sometime weight of the body, and d. And torque measured in the what is the force? Force measured in Newton, and this is a distance. So Newton meter is the unit of moment or torque, moment of force. Okay, it's simple. If you know the theta, the direction of the force, and how far you are applying the force from your main point, the pivotal point, you can calculate the torque. It's very simple. And balance and unbalanced. Let's say balance and unbalanced moment. Okay, the balance and unbalance. A torque is a turning effect. Either you turn in the left or turn in the right, or we can say there's two directions. One is the clockwise directions, and another is the anti-clockwise direction or counterclockwise directions. This is the opposite of the clock. Clock move like this one. Tuck, 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 tuck. This is the clockwise. And if something is moving in the opposite direction, tuck, 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 like this, it is called counterclockwise direction. Okay. And from that understanding, we can calculate the torque, turning effect of torque, or we can solve some problem related to the torque. And also we can solve the problem whether or not the system is in equilibrium. So how you can say that the body or system is in the equilibrium, right? In this case, you can say like the total clockwise moment is equal to the total anti-clockwise moment. Yes, this is the how we calculate the, or how we understand the system is in equilibrium or not. In this example, suppose this is the weight, right? The weight 200 newtons is in 1 meter from this point. Okay, and another thing says another weight, which is the 10 newtons, is 2 meter from this point, and we have to, and the force is in perpendicular distance. This is a perpendicular distance, perpendicular, right, with the length. This is also perpendicular. So we are going to calculate the, this is in the, this is this directions. This is moving in the counterclockwise, anti-clockwise. So the moment are in the clockwise and the anti-clockwise. Okay, now we are going to calculate it. What is clockwise moment? Let's calculate the clockwise. How much it is? Force into distance. Let's say F1, and which is, this is F1 and this is F2. This is R2 and this is R1. How much it is? 20 into 1, which is 20 Newton meter square. And what is this one? Clockwise, anti-clockwise, 10 into 2, which is 20 Newton meter. So in this case, clockwise and anti-clockwise moment are equal, so that we can say the system is in the equilibrium.